Okay, all right. So in this recording, we'll look at regression, right? So regression is again one of the basic topics and one of the basic tools used all through data science, including power systems, data science for power systems. So here, regression is normally you're given pairs of data, right? You're gonna think of X as the input, Y as the output. So for example, X can include, let's say, historical load, can include weather information, and different things. Let's say the Y that you want to predict or the output you want to have is the load for tomorrow. Okay, so you can have this type. So normally, the X, think of X as the data you have, Y is something you want to predict. And normally X and Y are vectors, right? So X has different components, X1, Xk, Y has Y1 to say Ym. So it could be multidimensional. And then we're going to assume there is some function that describes the relationship in y and x, and our goal is to find f, right? We want to find this function that describes them. So there's, regression is a basic way to do this, right? So the simplest one is probably least squares. Then we'll look at sort of various type of extensions you can build on the standard least square regression. So least squared answers the following question, right? So the two questions you ask when you're trying to fit data or you're trying to find a function from x to y, the first question you ask is, what type of function are we considering, right? So is it linear? Is it nonlinear? Is it polynomial? And then second you consider is, what exactly does good mean, right? So we want a good fit between x and y, but how do we measure good, right? So the notion of the goodness of fit is normally measured through residues. So you want your fit to have small error or small residues. And we're going to look at the first residue that we have, right? So we're going to look at the simplest case is where you have a linear function that you want to fit. So you think of y as a linear function of x. And then you think, and the least squares is when you measure the error using the square error, using the 2 norm. So linear means y equals to trans x, or y hat if we want to emphasize the fact that we're predicting, right? So we put a hat sometimes in the one on top of y to emphasize that y hat is a prediction. But often you'll see just that y equals to, we want to find y equals to w transpose x. So the w, this is the weight, and we're optimizing over w, right? So we want to find the best set of weight that will minimize some error. And the error we try to minimize is basically the least square error we try to minimize the difference between the y you observe versus the y that you predict. So the least square prediction is you're trying to minimize this, right? So this is the true y, this is the prediction, and you're trying to minimize this square error. You're trying to you want to minimize this as small as possible. So recall the definition of a vector squared. This is simply just a summation of all the components. So you square each component, you add it up. So the goal, right? So really to find the weights as you're given x1 to xn, you observe the data y1 to yn, and you compute this vector w, right? You say, okay, what is the vector that relates x to y and in fact minimizes error, right? So you want to find this weight. And then in this linear regression, actually, the reason we do linear regression is with square error, with least squares, is you can find the solution fairly easily. So this can be solved by hand. Okay, the way to see we can solve this by hand is, let's say, assume y is a scalar. So y is just a real number, right? So it's not a vector, it's just a real number. And our goal is to find a bunch of weights that minimizes this error. Okay. And this we can do by direct differentiation. And so this we'll do by direct differentiation. The reason we can do this is you can expand this thing out. This is just, right? So W is the one we want to find. Right? So we can write this. We can define a matrix X where we can stack all the data together. So we have n data points. We simply stack all of them up. We have Y. And then we can write this as, in matrix notation, the norm, the square norm. Okay, so Y is a vector, X is a matrix, W is a vector. And our goal is to minimize this norm by finding the right W. Right? So for given any W, you can calculate how large this number is. The goal is to find the W that minimizes this square error. And turns out this is very easy. Turns out the W that minimizes this is given by this equation. Okay, so you can see that if you want, you just directly do a derivative. Turns out this is the result that will minimize. So this will give you the smallest error. Okay, so the way we use it is basically given you have a bunch of data, right? So you have some pairs of data, and then you form X and Y, find W by using the above formula. Okay, so it's pretty easy to use, right? There's really not that much to it in this calculation. And what this gives you, it gives you, for example, the slope of this line, right? So slope of the line is W. So this basically lets you find the slope. Right? So, and you do this in the homework, right? And you give some data and try to find W, right? Try to find and you can minimize. You can find W by simply having the data X and Y, which minimizes the L2 error, right? So the error, this is called the L2 error. So there is again a closed form formula for this. Okay. So linear regression seems to be fairly trivial, present this way, right? So, but turns out it's actually quite useful, right? The reason it's quite useful is that we can have nonlinear functions. Okay? The only requirement is just that the weights show up linearly, right? There's no requirement that X has to be linear. For example, if you're given some data like this, let's say you have a bunch of data spread out this way, right? So this is obviously a nonlinear function. Let's say this dimension is x, this direction is y, and you have some data that's not linear. You can definitely fit a more complicated function than linear, right? So you can fit a function in the following form. You can use, for example, here a cubic function as your basis function. And in this case, the xi's can be, can be linear, can be square, can be cubic. For it to be a linear regression, the requirement that these weights enter linearly. Right? So as long as they enter linearly, then it's okay. Then then x's are not restricted to be linear in any fashion. Right? So x's can be very nonlinear. Right? So if you use different basis functions, again, basically the way you think about this is you have some function y, right? So y is a function of the weight w and the data input x. So y can be written in the following form. This is as you can sum up so these can be nonlinear functions. Right? So this can be nonlinear functions. If you want, one way to think about it is you have some data x and y. You can pass through this. You can do some pre-processing in x. You have phi x and y. And think of this as the new x, as the new input. And do linear regression. Okay, so you can do it this way. Again, it doesn't need to be, the basis function need not to be linear. Okay, so sometimes the basis function is clear. Sometimes the basis function, you have to guess around about. But the idea is that many different types of basis can be used. Right, so sometimes we can use, for example, polynomial. So you have things like beta 1 x1 squared. Or you have w1 x1 plus w2 x2, w2 x1 squared. Let me write this clearly. Right, so you can have w1x plus w2x squared plus w3x cubed, different type of things. You can have things like, for example, you want homework questions, you have following like sinusoidal functions, right? So you can have, for example, w1 sine of x1 of x plus w2 cosine of x, right? So these are perfectly fine basis functions. Right? So normally for different applications, it's up to you to, based on the application, to determine the basis that's supposed to be used. Okay, so there's a priori often not some set of best basis. As again, at different applications, you can look for different basis functions. Okay? And the solution is the same. Is again right? So again, you basically now think of this thing as the input. Okay, so before where y equals to x transpose x inverse, x transpose y, you basically substitute x to be this phi of x. Okay, so this is just a substitution. So you define a matrix, which is you evaluate all these input x, and then your solution is simply inverse. So there again nothing that's that much more complicated than before. Okay, so just if you have a nonlinear basis, then basically think of the input as as where you pre-process X, right? Then you compute the basis. Okay. And the reason of why again we use least squares is least squares is very simple. There is a closed form formula. It has a closed form solution. And for any other power, it's not we don't have a closed form formula. Right? So just the simplicity is much simpler in some sense than other cases. So one thing to note is for computers, this is not terribly important. Right? So you have other sort of norms, computer will solve it, right? For example, if your summation, if you change this to yi minus y hat, change the square to absolute value, you cannot solve this by hand. But to modern optimization software, it doesn't really make that much a difference. Right? The fact is whether you square this or not. But at least when you do analysis, having a least square is much simpler. And the second reason is that there is a clear statistical interpretation, right? This is sort of that there's a natural model where least squares is optimal. So in a very natural way to think the actual model is, the model is linear plus a little bit of noise, right? So we can measure x and y, we cannot measure this little bit of noise. Then in this case, it is, you can actually show that the least square estimate you get, right, where you compute the W this way, this is actually optimal in a sort of very clearly defined probability sense, right? There's a sort of very, in a sort of probabilistic setting, right? So we won't go too much into what this means, but this turns out least square is sort of the best you can do if we believe you have this sort of additive error, or additive Gaussian error at the end. And so normally when in practice, what happens is you at least try least square first. Okay? So of course, least square is not always optimal, right? It's not always optimal, but still, right? So one problem with least square is the fact that you have outliers. So for example, in this case, all the blue dots define it very clearly. There's a linear relationship, right? Goes through this. But let's say you have one point that is an outlier, that is a little bit, maybe you have a sensor error, or maybe there's a bug, or just something that's very rare happened once. You have this red dot. This single dot, the single point can actually pull your estimate of the weights, can actually change the estimate of the weights by quite a bit. Okay, so this can happen if you have a single, so this is called outlier, right? And so this means that the model is not terribly robust when you have this outlier. And so the next few classes, we'll see how to deal with outliers, how to change standard regression. But sort of what we cover in this short video should be enough for the homework for this week. Okay.